Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual ferment of the late 19th century, the vast and seemingly secure edifice of mathematics began to reveal subtle, yet profound, fissures in its foundations. The triumphant development of calculus and analysis, while powerful in application, rested upon intuitive notions of continuity, limits, and the very nature of number itself. This reliance on intuition, once a source of creative strength, became a cause for deep scholarly anxiety. The drive towards arithmetization, a movement championed by figures like Carl Weierstrass and Richard Dedekind, sought to rebuild analysis upon the bedrock of the natural numbers. It was into this quest for certainty that Giuseppe Peano, in 1889, introduced a small, 36-page Latin pamphlet titled Arithmetices Principia Novo Methodo Exposita. This work, whose title translates to the principles of arithmetic, presented by a new method, was far more than a mere summary of number properties. It constituted a radical re-envisioning of mathematical discourse itself, providing a formal symbolic language and a rigorous axiomatic framework that would fundamentally alter the standards of proof and become a cornerstone for the great foundational projects of the 20th century. Peano's new method was a declaration that the precision of mathematical thought demanded a language of commensurate precision, a language purged of the ambiguity and silent assumptions inherent in the immediate intellectual antecedent to Peano's work was Richard Dedekind's 1888 essay, Was sind und was sollen die Zahlen? What are numbers and what should they be? Dedekind, with philosophical depth, had provided a brilliant set theoretic construction of the natural numbers, defining them as an abstract system of simply infinite sets. He had successfully articulated the essential properties of the number chain, including a crucial principle of complete induction. Yet Dedekind's approach remained fundamentally descriptive. He used natural language, albeit with extreme care, to explain his concepts, persuading the reader through structured argumentation. Peano, reading Dedekind's work, recognized its genius but saw the potential for a more radical step. He sought to translate Dedekind's conceptual insights into a formal calculus, a symbolic machinery capable of generating mathematical truths through the manipulation of symbols according to explicit rules. Where Dedekind described the structure of arithmetic, Peano aimed to construct an engine for deriving its theorems. This ambition was also influenced by the earlier, though less widely known, formal systems of Hermann Grassmann, whose Orstenungslehr explored the creation of abstract algebraic structures from primitive elements and operations, prefiguring the axiomatic spirit Peano would bring to arithmetic. The revolutionary core of the Arithmetices Principia is its Novo Methodo, a comprehensive system of symbolic logic that Peano designed to express mathematical statements with absolute clarity. Before presenting his famous axioms, Peano dedicated the opening sections of his work to defining this new language. He introduced a suite of symbols that, while alien to his contemporaries, are now familiar to every student of logic. The Greek letter epsilon, for instance, was used to denote the relation as an element of. A reversed, capitalized letter C signified the concept of as a subset of, while a horseshoe symbol represented logical implication, meaning implies. He developed notations for logical conjunction and disjunction and, critically, for existential and universal quantification, allowing for the precise expression of statements like there exists an X such that and for all X. This symbolic apparatus was a breathtaking innovation. It sought to drain mathematics of rhetoric and intuition, replacing them with a universally intelligible and formally verifiable script. A proof rendered in Peano's system would be a sequence of symbolic transformations, its validity checkable with mechanical objectivity, independent of the psychological state or intuitive grasp of the mathematician. This constituted a profound philosophical shift, proposing that the essence of mathematical rigor lay in formal derivability. With this powerful logical machinery established, Peano proceeded to erect the structure of arithmetic upon an astonishingly minimalist foundation. He posited 9 axioms in total, of which 5 became the definitive characterization of the natural numbers. These 5 postulates, today universally known as the Peano axioms, distill the essence of the number system with unparalleled elegance. First, 0 is a number. Second, for every number x, there is a unique successor, denoted as x plus 1. Third, 0 is the successor of no number, establishing it as the starting point of the sequence. Fourth, if the successor of x equals the successor of y, then x equals y, ensuring that each number has a unique predecessor. The fifth and final axiom is the most powerful, the principle of mathematical induction. Peano formulated it with theoretic precision, stating that if a property holds for 0, and if, whenever it holds for a number x, it also holds for the successor of x, then the property holds for all natural numbers. From these 5 deceptively simple statements, the entire edifice of arithmetic could be rigorously derived. Peano demonstrated this by providing formal, recursive definitions for addition and multiplication purely in terms of the successor function. For example, the addition of a and b was defined by 2 rules: a plus 0 equals a, and a plus the successor of b equals the successor of the quantity a plus b. This demonstrated the immense generative power of the axiomatic method, showing how complex operations could be built from the most primitive of logical and numerical concepts. The reception of the Arithmetices Principia was, perhaps predictably, one of respectful confusion tinged with awe. For many working mathematicians, steeped in a tradition where intuition and geometric visualization were indispensable tools of discovery, Peano's dense thicket of symbols appeared as an obfuscating barrier. It was a language so austere, so divorced from conventional expression, that it seemed to some a form of intellectual fanaticism. The work's true potential was perceived by a select few who understood the foundational earthquake rumbling beneath the surface of their discipline. The most consequential of these few was the young Bertrand Russell. His encounter with Peano and his work at the International Congress of Philosophy in Paris in 1900 was an event Russell himself would later describe as a turning point in his intellectual life. Russell saw in Peano's logical calculus the precise instrument he had been seeking for his own ambitious project to demonstrate that mathematics was reducible to logic. He immediately adopted and began to adapt Peano's notation, finding it far superior to the cumbersome two-dimensional Begriffsschrift or concept script developed by Gottlob Frege. While Frege's work was arguably of greater philosophical and logical depth, its notation was profoundly impractical. Peano's linear, more algebraic symbolism possessed a usability that ensured its direct lineage into the mainstream of 20th century logic. The legacy of Peano's 1889 treatise is monumental, its influence radiating through the subsequent decades of mathematical thought. Its most direct and spectacular descendant is the Principia Mathematica of Alfred North Whitehead and Bertrand Russell, published between 1909 and 1913. This 3-volume magnum opus is the grand realization of the program Peano initiated. It takes the Peano's method of formal axiomatization and symbolic derivation and applies it on a breathtaking scale, attempting to derive the whole of mathematics from a set of purely logical axioms, while Russell and Whitehead introduced significant modifications to the notation and the underlying logic, particularly with their complex theory of types designed to avoid the paradoxes of set theory. The spirit of their entire enterprise is Peano's. The influence extends powerfully to David Hilbert's formalist program. Hilbert's goal of proving the consistency of mathematics by treating mathematical theories as uninterpreted formal systems is a direct intellectual heir to the Novo Methodo. Peano's work had provided the archetypal demonstration that a significant branch of mathematics could be free captured within such a formal system. This legacy culminates in the structuralist approach of the mid-20th century, epitomized by the collective known as Nicholas Bourbaki, the Bourbaki Project, which aimed to rewrite all of modern mathematics from a unified, axiomatic, set-theoretic perspective, represents the ultimate institutionalization of the Peano-Hilbert paradigm. The very structure of a modern advanced mathematics textbook, with its progression from axioms and definitions to theorems and proofs, is a testament to the revolution Peano began. In conclusion, the Arithmetices Principia Novo Methodo Exposita stands as a document of profound and transformative significance. Its contribution was a methodological revolution disguised as a technical treatise on arithmetic. Peano did more than simply list the axioms for the natural numbers. He forged the very language and established the procedural grammar for modern mathematical rigor. He championed a new ideal for mathematical truth, one where validity was synonymous with formal provability within a specified axiomatic system. This shift from an intuitive to a formal conception of proof provided the essential toolkit for the great logicist and formalist movements that would dominate the intellectual landscape of the new century. While few mathematicians today engage with Peano's original text or employ his specific symbolic conventions, the intellectual framework he constructed has become so foundational to the discipline that it is now almost invisible. It is the very atmosphere in which modern mathematical reasoning occurs. The slender 1889 pamphlet from Turin remains a powerful monument to the enduring idea that a fundamental change in method, a Novo Methodo, can reshape a field of knowledge as completely as any single discovery.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.